In this lesson, you will learn how to identify different transformations of functions. We will use function notation to help us write our answers of the transformations. There are three different types of transformations. There's a reflection, and that is from the a value. It causes the graph to reflect over the x-axis. There are translations. If it's an h value, it is a horizontal movement left or right, or if it's the k value, that is a vertical movement up or down. We can also have dilations of functions, and that is also using the a value. It can stretch a graph or compress a graph. So let's look at the first type of transformation, a reflection. It reflects the graph over the x-axis. Think about a mirror image or a reflection in the water. You see the same image reflected into the mirror or the water. So our function notation, we will have a negative as our a value. So let's take the original equation, y equals x squared. This is a quadratic function. If we want to transform the graph, making it reflect or open down, it now would become y equals negative x squared. We have here an exponential function, y equals 2x squared, and we see our graph. Again, if we wanted to reflect or make it open down, we would make our a value negative, meaning y equals negative 2x, 2 raised to the x. Let's now look at a translation. That is the h value, and it makes a horizontal movement left or right. But you have to be especially careful because we have to take the opposite. So let's look at that in our examples. If we have y equals x squared, let's say we want to take this graph and shift it to the right 3. Typically, that would be a positive, moving to the right. However, when we write our function, or even in function notation, we would put a minus 3. You have to be especially careful. You use the opposite. It went right, so we're going to use a negative. The opposite of a positive 3 is negative 3. Let's see it in our square root function. Here, if we took our graph and shifted it left 4, typically that would be a negative, but we're going to put a positive 4. And that does go inside of the function. Notice with our function notation, it goes inside with x because it's your x values that are changing. When it shifts left and right, that's your x-axis. Let's look at translations of the k value. That is a vertical or up and down movement. So we're going to take our function notation and add the k, and you will use the exact value. So we're pretty much taking our function and adding, or if it went down, subtracting a number. Let's look at our equations. We have our quadratic equation, y equals x squared. Our parabola currently is opened up, but if we want to shift that down 4, so it was at the origin, and shift it down 4, we would just say minus 4 using the exact value, y equals x squared minus 4. Let's look at our cube root function. If we have that original graph and it shifts up 2, we're going to add 2 to our function. And notice we just tack it on at the end, shown here in our function notation, because we're really taking our y values. Y stands for f of x, so we're taking our y values and adding k to that, adding the vertical movement or subtracting. So let's look at it all together. We want to transform the solid black function to match the dotted function. So we see our parabola currently as the solid black function is opening up, sitting at the origin. So this is our parent function, but we want it to change and become now the dotted red graph. So we first need to talk about our A. Well, because it's opening down, our A value is going to be negative. That's going to make it reflect over the x-axis. Then we need to look at our H. We want to make it shift 1, 2, 3, 4, 5 to the left, but we're not going to use -5. We've got to use the opposite. So we're going to say +5. Notice your notation. We want the opposite of H. So it went left. We want to do +5. Our K value, there's our left movement. Our K value, we will use the exact. So because the graph is shifted just down 2, we will use -2. So to write this out, just so it looks like our equation in function notation, it will be negative f of x plus 5. Remember, this goes inside because it moved along our x-axis where our x values would be. And then the -2 at the end because of that up and down movement. The negative out front is what makes it open down. We can actually write the equation of this function because we know this graph is quadratic. We can take our function notation and turn it into our quadratic equation. We have our negative a, we have our +5 for our horizontal movement, and we have our k for our vertical movement. Let's look at our next example. We want to transform the solid black function to match the dotted function. Notice, first of all, our a value will not need to change. It does not reflect over the x-axis, so we're going to keep our a value a positive. Our h value is that horizontal movement, and it looks like it goes 1, 2 to the right, but we're going to put the opposite, meaning a -2. Always be careful with that h that you use the opposite. Our k value will count 3, 6 up, so that will be +6, and you use the exact value for the k movement. So it does line up. So of course our simple way to write that function notation would be y equals f of, instead of plus and negative, we could just say minus +6. Because this is a square root function, we could write it in the square root function format. Square root of x minus 2, that's our function, and that +6 on the outside for our vertical movement up and down. Let's look at another one. Be especially careful. The original function may not be the parent function. We have seen in the last 2 examples that our original graph started out as the parent function at the origin. Notice this graph is already transformed. It went left and up off the origin. So this is not the parent function. There's already been some transformations occur, but we still want to get it lined up with the dotted function. Think about your a value. We will need to make it negative so that it can open down. Our h value is the horizontal movement, so count 1, 2, 3, 4, 5. Notice we did not count from 0. We counted from where the point of this absolute value started. So I went 5 to the left. So of course we're going to put the opposite, meaning a +5. To the left is normally negative, but we're going to do opposite and put a positive. Our k value is the up and down movement, and we need to go down 1, 2, 3, 4, 5, 6. So down 6, and we'll use the exact value. So we could write this function notation, just y equals negative f of x plus 5. Remember, we used the opposite. It went left, so we used positive 5. And then down 6, we used minus 6. The equation, it is possible to write the equation of this, but we couldn't use it from this function notation because we would have needed to know the original function, how it started with that transformation to write our new transformed function. Let's specifically look now at our parabolas. This is our main focus of Math 2, so let's talk even more in depth with our parabolas and their a values. So if we have the standard form of a parabola, which is ax squared plus bx plus c, our a value does tell us that the graph is going to have a reflection or not. It can reflect over the x-axis, whether the graph opens up with a positive a value or the graph opens down with a negative a value. So that will tell us about our reflection. But also with a parabola, we can have dilations. It's that vertical stretch or compression of the graph. So when we stretch it out, if you imagine a rubber band being stretched out, it gets real tall and skinny. Or also if you even compress, if you think about smushing a hamburger flat, it flattens it out. So that we can see here with our graphs as well. If we have an a value of 1, there's no change to the graph. It's that regular parent function, no change has occurred. But if our a value, now we do use absolute value so that we're not worried about positive and negative, because that positive and negative, we've already said, that causes the reflection. But a positive the absolute value of your a value, if that comes out to be greater than 1, it's going to stretch that graph out, and notice how it makes it real tall and skinny. So an example of an a value that would do that would be like an a value that equals a 6, or an a value that equals a 9. All of those are greater than 1, and it would stretch that graph up real tall. So we can also have a compression of our graph, and that would mean that our a value is between 0 and 1, again, meaning the absolute value, because we're not worried about the positive or negative. That causes the reflection. We just want to talk about the absolute value of our a being between 0 and 1. So really, a fraction or a decimal. That's going to compress your graph. It's going to smush it. So if you think about smushing a hamburger, it makes it flat. It flattens it out, okay? So let's look at some examples. We're going to match the appropriate a values to the graph. So here are our choices and our graphs that we're going to match it to. Notice 2 of our choices have negative a values, so those are going to open down, where this one with a positive 1, we know is going to open up. So I'm actually going to match that one first. A equals 1, I know has to be this graph because it's opening up. And notice too, this graph has no change. That is the regular U shape. Although it is cut off, it's not stretched up real tall, and it's not smushed down real flat. So now we've got to determine between the last 2. We have a negative 0.25, so that is a decimal between 0 and 1. And then this 4 is greater than 1. And again, at this point, we're just looking at the value, the absolute value of those a's, not the negatives, because we've already determined that's making it open down. So the negative 0.25, that's going to be this first graph. We can see it's kind of getting smushed, even though it is turned upside down. And then the negative 4 will go here on this graph because it's stretched out that parabola nice and tall. Let's look at the next set of graphs and their a values. So again, we can kind of process of elimination narrow down our choices. We only have the one that has the negative, so I match that one first. We know it opens down. Looking at the other two options, we have 0.25 and 4. So once again, the 0.25 is going to be more smushed vertically, and that 4 is going to be more stretched vertically. So the compression and stretched are based on the A value, whether it is greater than 1 or between 0 and 1.